In this video, we're going to use calculus to help us graph and understand families of functions. Number one, f sub a of x equals x cubed plus a times x. This notation may be a little strange to you. The subscript there for the function f tells me that a here is a parameter. I think about this function for constant values of a, but then what's most interesting is to ask what happens as the parameter a changes. We want to use calculus to analyze the graph and understand what happens as a changes. There's one function and one graph for each of the infinitely many possible values of a. In particular, we want to describe how any critical points and inflection points of the graph change as a changes and help us actually draw that. We'll also use Mathematica, technology, to help us visualize this. So how do you use calculus? You've got to take the derivative. F sub a prime of x. By the way, your book may not use a subscript here for the function. It's okay. I like using it to emphasize it does depend on a. I take the derivative with respect to x. I treat a as a constant. So I get 3x squared plus a when I differentiate with respect to x. Set this equal to 0 and solve for x to find critical points. Now you may be thinking to yourself, well, that's never 0 because a is positive. Well, you're making an assumption there. You're making the assumption that a is positive. In reality, a could be negative. The derivative could be 0. When we solve for x, we get 3x squared equals negative a. That means x squared is negative a over 3. And that means x is the square root, or plus or minus the square root, of negative a over 3. If a is a negative number, then negative a, the opposite of a, is a positive number, and so is negative a over 3. We're taking the square root of a positive number. In such a case, we do get a real number. So we're going to have critical points when a is positive. Actually, when a is 0, we get a critical point at 0. So we have critical points here, real critical points, you might say, when a is less than or equal to 0. No real critical points when a is positive. So that is telling us something about the graph. It's saying somehow we have critical points when a is less than or equal to 0, but none when a is positive. That does affect the graph. What about possible inflection points? Take the second derivative. We get 6x plus 0, just 6x. It doesn't depend on a. A does not affect possible inflection points. To find those possible inflection points, we set this equal to 0 and solve for x. And we get x equals 0 as a possible inflection point. Is it an actual inflection point? The sign of the second derivative needs to change at the possible inflection point. Does it? Yes, 6x does change sign from negative to positive as x increases through 0. Also, we can think about the nature of the critical points here and whether they give local maxes or mins. If we assume we're in the case where a is strictly negative, so we have two distinct critical points, one at negative square root of negative a over 3, and one at positive square root of negative a over 3. Make sure you say that right. And think about the sign of this derivative here. What is the sign of f prime in each case? Well, okay, if a is negative, we're in the case where f prime of x is 3x squared plus a negative number, which means 3x squared minus a positive number. That's a function whose graph is a parabola opening upwards. It's going to be certainly positive over here, and negative in here. You could plug in 0 if you wanted to make sure. 0 squared is 0, 3 times 0 is 0, 0 plus a is a. And if a is negative, then f prime of 0 is certainly negative. Over here, f prime of whatever you plug in over here will be positive. Same thing when you plug in a number over here. This means f itself is increasing in this window, decreasing in this interval here, and increasing over here. So we have a local max there and a local min there. You could know that also by thinking about the fact that this is cubic with a positive leading coefficient as well. So in the case where a is negative, the graph is going to look like this. It also goes through the origin. It's also an odd function. You can pretty quickly surmise from that the graph is going to look about like this. It's got origin symmetry there, and I'm not drawing it perfectly, but halfway decent graph there. This is the negative critical point at negative square root of negative a over 3. This right here is the positive critical point at positive square root of negative a over 3. An inflection point at 0. If you want, you could also possibly find the x-intercepts. That would be found without calculus just by factoring, if possible. In this case, it does look possible. X times x squared plus a, and the x-intercepts are going to be at, let's see, this would be, in the case where a is negative, we got x squared minus something. That would be x squared, x minus the square root of, let's see, negative a, I think it would have to be, in the case where a is negative, times x minus the square root, or plus the square root of negative a. That may seem a little odd, but if you check it by multiplying it out, it really does work. The x-intercepts are at 0, where the inflection point is, and this point is negative square root of negative a, and this point right there is positive square root of negative a. What's going to happen as a increases to 0, in the case where a equals 0, well, the function is just x cubed. These points, these critical points, and in fact the x-intercepts are going to all have to merge toward the origin. When a is 0, the graph is the graph of x cubed, like that. And when a is positive, there are no critical points, no real critical points at least. There are imaginary critical points, imaginary numbers. And also, if you think about it, the first derivative in that case, when a is strictly positive, is always going to be positive. The function's always going to be increasing and, in fact, always have a positive slope. It's going to look more like this. But there will still be an inflection point at the origin in all these cases. By the way, here in the case where a equals 0, there is still a critical point at x equals 0. The tangent line is still horizontal there, but it's neither a local max nor a local min. Let's use technology, Mathematica in this case, to confirm this, to visualize this. So this is a graph when a equals negative 4, and if I play it here, we see how the graph changes as a changes, and when a is 0, the critical points merge to the origin, as well as the x-intercepts. They all go toward the origin, and that origin, which is green, is an inflection point no matter what a is. For number 2, the family of functions is f sub a of x equals x squared plus a over x. Once again, the directions are to use calculus to analyze how the graph of these functions changes as the parameter a changes. Again, for any fixed value of a, you get one function and one graph, but what's most interesting is thinking about what happens as a changes. In particular, again, describe how any critical points and inflection points change as a changes. So once again, we take the derivative, f sub a prime of x. With respect to x, treat a as a constant. Realize a over x is the same as a times x to the negative 1, so we can avoid the quotient rule if we want. When we differentiate this, we get 2x minus a x to the negative 2, which is the same as 2x minus a over x squared. We're looking for critical points. We set this equal to 0 and solve for x. We'd add a over x squared to both sides to get this, and then multiply both sides by x squared and divide both sides by 2 to get x cubed is a over 2. And that will mean x, your one critical point, which will exist no matter what a is, will be the cube root of a over 2. Okay, so when a is positive, that's a positive cube root. When a is negative, the cube root of a negative number is a negative number. The critical point changes, well, as a increases from negative to positive, the critical point itself changes from a negative location to a positive location. This is the critical point. Though, we should keep in mind that when a is 0, the function is, it's a little strange. This part goes away, and it's just the x squared function. And this still does end up being a critical point. This graph has a vertical asymptote if a is non-zero, but no vertical asymptote if a is 0. That's kind of weird. You might wonder how that happens. How are we going to visualize this in Mathematica? For possible inflection points, we take the second derivative, we'll get 2. Take the derivative of that, we'll get plus 2a x to the negative 3, which is the same as 2 plus 2a over x cubed. Set that equal to 0, and solve for x, you'll get 2 over x cubed equals negative 2. Excuse me, 2a over x cubed equals negative 2. That'll mean multiply both sides by x cubed and divide both sides by negative 2. X cubed will be negative a. The 2's will cancel. And then that means x itself will be the cube root of negative a. If a is negative, then negative a, the opposite of a, will be positive, and the inflection point will be at a positive x location. And if a is positive, then negative a is negative, and the cube root of that will be negative, and the inflection point will be at a negative location. Is it truly an inflection point? Does the second derivative change sign? If you think about graphing this with technology, perhaps, I think you'll see that it does change sign at that value of x. I'm pretty sure that's going to happen. What about the critical point? Is it a max or min? Actually, we could think about the second derivative test. When we plug in this critical point into the second derivative, let's go ahead and do that here. F sub a double prime of the critical point, cube root of a over 2. It's kind of nice because it's got an x cubed in there. You're going to get 2 plus 2a over, this thing cubed is going to be an a over 2. The cube root's going to go away. When you simplify this, the a's divide out. 2 divided by 1/2 is 4. We get 6, which is positive. So the graph of f sub a is concave up near the critical point. It will be a local min, evidently no matter what a is. This doesn't depend on the value of a. So what about the graph? Let's think about different cases. Let's start with a negative. You should probably think about the possibility of x-intercepts as well. If I set x squared plus a over x equal to 0, the function itself equal to 0, that gives me x squared is negative a over x, and x cubed is negative a. And how about that? That must mean, if I haven't made a mistake here, double checking things here, that the x-intercept is at the same location as the inflection point, cube root of negative a. That's kind of interesting. That's unexpected, you might say. We're adding x squared and a over x. It might be helpful to also think about adding those individual functions graphically. So let me use different colors here. So let's use the green for the axes. Let's graph x squared, first of all, and we'll make it dashed in red, like that. That's y equals x squared. Let's also graph a over x when a is negative. A different color here. A over x when a is negative is going to look like this over here and this over here. That's y equals a over x in the case where a is negative. And we're adding these two graphs to get the final graph. Again, when a is negative, the x-intercept is positive, the inflection point is positive, but the critical point is negative. And there's a vertical asymptote at x equals 0. Okay, can we put all this information together? Again, the x-intercept is positive. This stuff, adding these two graphs over here, this part wins out over the red part. The graph is going to be down here. It's got to cross the x-axis somewhere at an inflection point. This graph is going to change concavity, it looks like, from concave down to concave up. That makes some intuitive sense. That point right there has got to be at the cube root of negative a. It's got to look like that. And add graphs over here, it's going to have a vertical asymptote here, come down, and yeah, have a minimum. It does seem, yeah, the second derivative is positive here at the critical point. It's hard to say. It's not necessarily going to be where they intersect. It could be slightly different, the x value. I'm not going to say exactly where it is here. Something about like this. This point right here would be the critical point. This would be the cube root of a over 2. It would be, yeah, okay. This looks, it would be closer to the origin than this one is. So something about like this is what the graph looks like when a is negative. When a equals 0, it's the x squared function. So somehow, as a increases towards 0, it's like the pieces of the graph somehow have to merge for an instant into the x squared function. Interesting. We'll have to see how that happens on Mathematica. And then when a is positive, the x-intercept as well as the inflection point becomes negative, and the local min location becomes positive. We could also think about adding the graphs again of x squared, which is constant, doesn't depend on a, and a over x, in the case where a is positive, looks like this. So now we're adding these graphs. That's y equals a over x, and once again the red graph here is y equals x squared. And sort of the reverse of what happened over here seems like it's probably going to happen here. Graph is going to go like this, say, when x is positive, and your minimum, your critical point is at the cube root of a over 2 again. And when x is negative, it's got to look something like this. And let's see. The x-intercept is an inflection point. That's at cube root of negative a. Yeah, it's sort of the reverse kind of thing happened compared to this graph. Let's go ahead and see this in Mathematica now. See this happening. The critical point is in blue, the inflection point is in green. And yeah, as a crosses through 0, they kind of merge and flip. When a equals 0 exactly, it is the graph of x squared. Okay? So that's pretty interesting. For problem 3, we continue this, I think, fun subject with the situation where we now have two parameters. F sub ab of x equals a times x times e to the negative bx. We have two parameters involved. It would be interesting to see how this graph changes as both a and b change. Yes, as both of them change, in particular describing how critical points and inflection points change as a and b change. All right, so two subscripts, and again, some books would not even bother with the subscripts, but I think it's good to emphasize that this is a family of functions, in this case, a two-parameter family of functions. A and b are constants. We differentiate with respect to x. I do need the product rule. I've got a left function, a times x, and a right function, e to the negative bx, or first and second functions if you prefer. The product rule you could say is left d right plus right d left, or yeah, the derivative of the first is what I usually like doing. A times x, its derivative is a, times the second function, e to the negative bx, and then plus the first function, ax, times the derivative of the second. The derivative of e to the negative bx is e to the negative bx times negative b by the chain rule. As always, it's good to factor as much as possible. We can factor out an a e to the negative bx out of these two terms. What's left over in the first term is 1, and with the second term is going to be minus bx. Factoring helps us see where this is going to be 0. I set this equal to 0 and solve for x. This is never 0, so this means 1 minus bx is 0, which means bx is 1, which means x is 1 over b. So there's your critical point, at least as long as b is non-zero, because then you'd be dividing by 0. It's a critical point that if b is positive, and say very, very small, like 0.1 or 0.01 even, this critical point is going to be a very large positive number, but as b increases, it's going to head towards 0, right? If b is 100, this is 0.01, for example. So this critical point is going to move toward the origin as b increases away from 0. If b is negative, it's negative, and sort of the opposite thing happens as b decreases away from 0. This goes from being a large negative critical point to a small negative critical point close to 0. Kind of weird. I guess as b increases overall from large negative values to close to 0 to small positive values to large positive values, I guess this critical point would have to move to the left, being negative, off to infinity, I guess, and then it would have to move back toward the origin through positive values. Kind of weird behavior, you might say, I guess. Is it a local max or a local min? We could think about the first derivative test. It depends on the sign of a, I guess. If a is positive, and you think about doing the first derivative test, 1 over b, b is non-zero. Let's see, I guess we have to think about the case where the sign of b as well. A is positive and b is positive. Then that's a positive quantity, that's a positive quantity, and this is a quantity that changes sign from, if b is positive, if you're less than 1 over b, like 0, for example, that's a positive quantity. And if you're bigger than 1 over b, imagine plugging a number bigger than 1 over b in here, like 2 over b, you're going to get 1 minus 2 in that case, a negative number. So the function itself changes from increasing to decreasing, and you've got a local max. That's probably the case of most interest, right, for applications, is if a and b are both positive. I think I'll stop the analysis there. With Mathematica, we'll see what happens maybe when a and b are negative. But of applications that would be most interesting in this case, and it would be a local maximum at x equals 1 over b. As far as inflection points go, now find the second derivative. Perhaps, I mean, you could take the derivative either in this form or this form. Let's go ahead and use this form. So the derivative of a e to the negative bx will be negative ab e to the negative bx. I just used the chain rule there. And the derivative of this, I need the product rule for again. Got a minus sign that I can bring in front. Let's be careful with it here. So I'm bringing that minus sign in front, then taking the derivative of abx, which is just ab, times e to the negative bx, and then abx times the derivative of e to the negative bx would give me this. That's pretty tricky. You got to be really careful. I believe I did it right there. The minus sign here I brought in front to begin with, that corresponds to this minus sign. Simplify, distribute this minus sign through, you get these two terms are the same, so you get minus 2ab e to the negative bx. Distribute the minus sign through over here, the two negative signs cancel. Looks like you get plus ab squared x e to the negative bx. Factor out as much as you can factor out. We can factor out an a b, and an e to the negative bx. And what's left over with this one is a negative 2. What's left over with this one is a plus bx. I think I did that right. Set that equal to 0 and solve for x to find possible inflection points. That's never 0 as long as a and b are non-zero. So we only focus on when this is 0, so that's going to imply bx equals 2, which means a possible inflection point at x equals 2 over b, twice the value of the critical point. And it will be an inflection point when a and b are positive. The second derivative will change sign. It is an inflection point when a and b are positive, at least. You could think about the sign of the second derivative. If a and b are positive, this is positive. If you're less than 2 over b, like 0, this is negative. The graph will be concave down, the graph of the original function, because the second derivative is negative. And as x gets bigger, this becomes positive, and the graph becomes concave up. So in the case where a and b are both positive, you can also think about the fact that this function is going to be negative in value when x is negative, positive in value when x is positive, and in fact, as x goes to infinity, when a and b are positive, this goes to 0, and b is positive for sure. The graph is going to look like this. It does go to minus infinity as x goes to minus infinity. If a and b are positive, you've got a quantity going to minus infinity and a quantity that's going to plus infinity. The product is going to minus infinity. It's going to look like this. Your critical point is a maximum, like I said before, by the first derivative test. That's at 1 over b. And your inflection point is right here at 2 over b. Sorry. As b increases, if a is constant, these points are going to head toward the origin. I guess the graph gets more scrunched up for a constant value of a as b increases. It's hard to say whether the graph goes higher or lower. I guess we could plug 1 over b into the function and see what happens. F sub a comma b of 1 over b, going back to the original formula. Up here, replace x with 1 over b. I'll get a over b, e to the negative b times 1 over b is e to the negative 1, so this becomes a over eb. If a is constant, as b increases, this gets smaller and smaller. So I guess the output of the location of the maximum gets smaller as b increases, as it also goes toward the origin here. That's a larger value of b for a constant value of a. How does a affect things? As a increases, if you think about it even just intuitively with the original formula, the graph is going to go higher if a is positive. For a fixed value of b, increasing a will make the graph go higher. You can see that when you think about the output of the function here. A is in the numerator. That gets higher as a increases. So let's confirm this now with Mathematica. Ignore that. Got positive values of a and b here by default. If b increases, the graph goes toward the left, those points toward the origin overall for a fixed value of a. And if b stays constant and a increases, yes, the graph goes up. What happens if a is negative, for example? Well, it just flips across the x-axis. If b becomes negative, you get this kind of behavior. And if both of them are negative, you get this kind of behavior. And I'll let you take the time to think about that. Our last problem, we have a function of two parameters that is the product of an exponential decay and a sinusoidal function in the situation where a and b are positive. That's not stated here, but I'm going to assume, for sake of simplicity, like in the last problem, that a is positive and b is positive. This is an important kind of function that arises in many applications. One particular application is a mass in a spring oscillating with some friction. The oscillations arise are modeled by the sine function, and the friction is modeled by the exponential decay. E to the negative ax is an exponential decay in that oscillation over time, if x is time. The amplitude of the oscillation gets smaller and smaller. Okay, so this is a pretty important kind of function. Use calculus as before to analyze what happens to these functions as a and b change. We won't be able to fully analyze this. We want to keep things as simple as possible. Mathematica really will be a big help to us here to more fully understand what's going on. Let's focus on understanding the first couple non-negative critical points and how they change as a and b change. But again, a full understanding really will require technology. It's pretty hard to do without technology here. Okay, I'm not going to focus on inflection points because that's just going to make the video too long. But it does have an inflection points, and I would encourage you to see if you can figure them out. So we take the derivative, and we need the product rule plus the chain rule. The derivative of the first function, e to the negative ax, is negative a e to the negative ax times the second function, sine of bx, plus the first function, e to the negative ax, times the derivative of the second function. The derivative of sine of bx, where b is a constant, would be b times cosine of bx. I'll write that as cosine of bx times b. We want to find critical points, set this equal to 0, and solve for x. Doesn't look so easy. Can you factor anything out? Yes, you can. You can factor out an e to the negative ax, which is never 0, so that's nice. What's left over in parentheses is negative a sine of bx plus b cosine of bx. So the only way this is 0 is if the part in parentheses is 0. And what I find simplest to do to try to solve for x here is rearrange so sine is on one side and cosine is on the other, and then divide both sides by the cosine to get the tangent function involved. So if I add a sine x to both sides, I'll ultimately get a sine bx equals b cos bx. Just make sure I didn't make a mistake here. I think that's all right. And divide both sides by cosine bx to get a tangent bx on the left, and also divide both sides by a. Tangent of bx equals b over a. So we could solve for one value of x by now taking the inverse tangent function, applying it to both sides to say bx is inverse tangent of b over a, and divide both sides by b, you'll get one answer. I'm after the first couple non-negative critical points here, not just the first non-negative one. So I'm going to think about a couple possible answers here. Bx could be, after a couple positive answers here, the first couple positive answers, in the case where a and b are positive. It could be the inverse tangent of b over a, which is the same, by the way, as the arctangent of b over a. Inverse tangent and arctangent are the exact same function. We also could do inverse tangent of b over a using the fact that the tangent function is periodic with period pi, not 2 pi. We could add pi to it. I could keep going if I wanted more solutions, but I'm after just the first two positive solutions. Now divide both sides by b to get the value of x. 1 over b inverse tangent of b over a, and also 1 over b inverse tangent of b over a plus pi over b, and I could also write that as one fraction, but because there's already a common denominator of b. So in terms of a and b, these are the first two positive critical points. Do I want to use the first or second derivative test to figure out whether they are maxes or mins? I could. I think I don't want to. I could think about where the first derivative changes sign here, how it changes sign from positive to negative or negative to positive. Actually, it might be simplest to think about the original function. F of 0 is 0 because sine of 0 is 0. And f of a slightly positive number will be positive because that'll be positive and that'll be positive. So you will get a positive quantity. The first critical point's got to be a max. And the second one evidently would have to be a min. But the easiest way to think about that seems to be thinking about the original function. The first and second derivative tests seem difficult. It seems difficult to think about how the sign of this changes, though in theory you could. It also seems difficult to think about taking the second derivative, though we could, and plugging these critical points into that. This is where we're really relying on technology. It's also difficult without technology to think about how these changes, b changes and or a changes, partially because the inverse tangent function is an increasing function of an increasing input, but we're dividing by something that also increases as b increases in this case. So it's difficult to tell whether this increases or decreases without technology. Now, you can reason it out in a vague kind of way, not real precise. Yes, inverse tangent, the arctangent function, does increase as b over a increases. Say a is fixed and b is increasing. But it does have a horizontal asymptote. It never gets bigger than pi over 2, in fact. Whereas you're dividing by something that gets arbitrarily large. That's some intuition saying this should be probably something that decreases for fixed a as b increases. For fixed a, as b increases, this quantity should decrease. This critical point should go towards 0. And the same kind of thing is going to happen with this critical point. So for fixed a, as b increases, the critical point should go towards 0. That makes sense if you think about this fact, this oscillating, and b affecting the period of the oscillation. As b increases, it's going to be a faster and faster oscillation. Those critical points got to get scrunched toward x equals 0. That makes intuitive sense. What about for a fixed value of b as a increases? That's actually a little simpler. If b is fixed, that's fixed. You got inverse tangent of a fixed number over something that's getting bigger. The fraction here is getting smaller, therefore its inverse tangent is getting smaller. You're also going towards 0 as a increases. As a increases, the critical point locations are going towards 0. The period of the oscillation, so to speak, is the same for fixed b, but the fact that it's decaying more rapidly somehow is making the x-coordinates of these critical points still decrease. That might still feel a little funny. Let's go ahead and now just end the video by confirming this with Mathematica. So now I've marked off the first two critical points. Okay, so A is 0.5 and B is 1 to start with here. If I let A be fixed and just increase B, yes, it's a faster and faster oscillations. The x-coordinates of those critical points are going towards 0, though their y-coordinates are going further away from 0. If I keep B fixed and increase A, it's a faster exponential decay, and yeah, you can see the x-coordinates of those points going towards 0, though more slowly as A increases. But it does seem to be happening here. The distance between these x-coordinates seems to be staying relatively constant. I guess that makes sense if B is fixed because the period is still staying the same. This one's going to 0 for fixed B as A increases, but this one is not. It's going toward pi over B. Okay? So I didn't think about that until just now, but that is what's going on. I hope you enjoyed this. Thanks for watching.